Okay, let's get started. See, we are going to work on nonlinear optics. This is an extension of lasers in one area. This has limited range of frequencies. So if I want to have another domain of laser wavelength, I go for nonlinear optics. To do proper understanding, first you must state what is the basis of mini lasers. Now, you can get laser from gas, liquid, solid. The media is different, but the principle is only one. For example, I take a gas. Simplest example is helium neon gas. Put it at low pressure, then I produce a discharge. When I produce a discharge, that's all for schematically. This may be about 2000 volts. Then you have electron running back and forth here. Okay, then since atoms are running back and forth, the electron which goes from here to here will hit the atom, produce excitation. When it produces ordinary excitation, you will have spontaneous emission coming from everywhere. This is how ordinary light, like a neon lamp. In Bata, you will see the same neon lamp, same idea. Then, what do we do for laser? Next step is, you produce intense excitation so that you produce population inversion in neon atom. This is done by simple process. You do electron, hit helium, then helium gets excited, helium gas. The helium gas which is excited hit neon which is sleeping in the ground state, and neon gets excited. Then neon gets excited, produce photon and goes to the ground state. This is the process of helium neon light, not the laser first. Helium neon light, first step. Second step, if the excitation is really strong, you will have plenty of atoms in the excited state of neon. If we have more atoms in the excited states of neon, let me say this is 60, this is only 10, you have produced population inversion from here to here. This is N2, this is N1, N2 is greater than N1. Under this condition, the light photons which are produced by this one, you will have two types, spontaneous emission, and then the spontaneous emission act as a seed to produce stimulated emission. The stimulated emission will be preferentially in this direction. So, the spontaneous emission photon starting from this will become stimulated photon. This stimulated photon will produce more stimulated photon, more and more. Then you will have stimulated emission in this direction. Look at this one, in this solid angle. Then I put a mirror, This is 100%, this is also 100%. Then what would happen? The stimulated photon going here will be reflected back. When it reflects back, it comes and produces more stimulated emission. In that way, in this small pattern, you will have stimulated emission and spontaneous emission. But stimulated emission will be more than spontaneous emission. The spontaneous emission is the seed starting from there. But stimulated emission, growth will be more. So you will have plenty of photons which are stimulated photons in this region. If this is all the condition, if this is 100%, this is 100%, you will have plenty of stimulated photons within this resonator, and it is useless. Because it is something like very good soldiers kept within the fort. What is the use of this? And they should go and fight. So what we do, instead of 100, we keep it 9%. Then 10% of the stimulated photons will come out as a laser output. 10%. Now this 10%, since it is coming out, you must keep on producing more and more population person to compensate for the 10%. Only then you will have continuous release of stimulated photons. The stimulated photons are the coherent photons, they are the laser photons. So it's a constant process since you are taking constant output. That is how a helium ion laser there works. Okay. This is a principle of any type of laser. Let us see a stock taking of a variety of lasers before we go into nonlinear optics. Only then you will understand the importance of nonlinear optics in proper perspective. Helium ion laser is a gas laser. Now let us do stock taking. We said there are three types of medium. The fourth is the plasma. So we have, let us say, gas. In the gas lasers, you have the most important is the Heine laser. This has 25 milliwatt power, that's all. CW, wavelength is 63.28 nanometer. The next important is argon ion laser. Remember, this is a helium, neon, neutral gas. This is an ion. And this produces laser. It can be from 1 to 5 watt. Remember, 5 watt, this is 25 milliwatt. This produces many lines. The most important line is 488 and 514.5 nanometer. And remember, this is again CW. Next, this argon ion laser is that one. That's an argon ion. That long one is an argon ion laser. Sometime next week, you remind me. I will open up and show you. I will open up that one. I will open up Heine laser. I will open up and see what is there inside. Okay, next time. Next important laser is a CO2 laser. This produces laser at 10 point, look at this one, 10.6 micrometer. This is in nanometer, this is in 10.6 micrometer. This is an infrared laser, and this produces laser easily from 1 watt to 100 kilowatt. Let's say 10 kilowatt. It's a very, very powerful laser. It's a high power laser. We have seen all this many times. And then, next is nitrogen laser. This is CW, CW, CW. It If you want to get a pulse laser from this, you cannot get it unless you do mode locking. We are not touching about mode locking. This cannot be Q-switched. This cannot be Q-switched. Both can work only as a CW mode, but it can be mode locked. All the details I don't want to go further. Coming back to this one, this nitrogen laser is a molecular laser. This is also molecule. This is an ion. This is a neutral atom. Look at this one. You have all the 4 varieties now. Neutral atom, ion, a molecule. This is also molecule. This nitrogen molecule is a very crazy one. This will be always pulsed. You cannot make it CW. This will work only for 10 nanoseconds or even less. The pulse width is about 10 nanoseconds. And the energy is about 1 millijoule to 20 millijoule, not more. Next one. Next important is excimer laser. You have seen this one. In excimer laser, you can have argon chloride, argon fluoride, xenon chloride, xenon fluoride, like that. You have all possible combinations. All of them are ultraviolet, pulsed, high power laser. High power laser. Like this is typically 20 nanosecond. This is look 20 millijoule. Compare this one. This can be even 200 millijoule. Can be 200 millijoule. When this laser operates, maybe you will not have an occasion to see this. The laser operates if I put a brick, you know brick, cement. If I put it, you will see the smoke coming out. So you can see the reddishness from the heat produced by this laser. It's a very powerful laser.
You see smoke.
Yeah, it will come. You put your hand, tuck, tuck, you will see the smoke coming. This is the laser. This is the excimer laser. You have Hini, you have argon, this is the excimer laser. They are all dead. Okay. This is what I call, I would say this is the fat. I have opened up all the product in the gas lasers. Most important. There are some more, we don't care about them. But these are the most common lasers in many of the laboratories, and every one of them can be bought. What I mean say is, if you just go, if you have money, place order today, you will buy this. There are certain other lasers which are in the laboratory. You cannot buy. They will work only for the researchers' science. So other things you don't care. Next one. The other one, from the gas, we will go to liquid. In the liquid, you have only 2 types. This is the dye laser, and the other one is a conjugate polymer laser. Conjugated polymer laser. The dye laser is a single molecule. In the conjugated polymer laser, it is a polymer, one molecule tied to another molecule, tied to another molecule, like that. Few thousand molecules are tied, and then it becomes a polymer. If you properly prepare this kind of polymer, this will behave very much like a dye laser. The biggest advantage of these two are both of them are in liquid solution. First step, second step. So they are tunable. Tunable means take one solution, one dye laser solution, you can just tune the grating as if you tune your radio, and then you can get a laser from 420 nanometer to 520 nanometer very easily. Just like that you can tune. Since it's a liquid solution, you don't have to bother too much to cool it. You can circulate that liquid solution, so the circulation itself will produce enough cooling, so you will get a very efficient, very high power, tunable laser. The speciality, the significance of dye laser or conjugate polymer laser is tunable laser, because most of the gas lasers are not tunable. That is where it becomes very important. Most of the gas lasers are not tunable. Okay. Whatever I said about dye laser is very similar to conjugate polymer laser. So you do the same kind of preparation, everything. The big difference between, look at this, gas laser and the liquid laser is, for gas lasers, the only way to produce population inversion is electrical discharge. All this I have told you in my earlier paper also, because this is the starting point or introduction for any kind of laser paper. You should know all this, then only you can go to the next step to have a proper understanding. This is electrical discharge, whereas here this is optical pumping. Optical pumping. Now, using different types of dye solution conjugate polymer laser, one can get a laser from, let us say, 400 to 800, let's say 1000 nanometer. That means I can tune the entire visible range by a combination of different dye solution and different conjugate polymer. You can play around. Okay, next step. Yeah, the power, one more thing. The power from these kind of lasers is usually, one more. These can be pulsed or CW. Look, and CW. When I say and or, I can play around. I can make it CW or pulsed.
The dye and the conjugate?
Yes, conjugate. Now, right now, dye solution, yes. Conjugate polymer is not at CW. This is what is those people, Prasad and other people are doing research. Dye solution, CW lasers are available in the market.
But it is not pulsed.
Which one?
Dye.
It can be pulsed also. It can be pulsed or CW. Whereas conjugate polymer, right now it is only pulsed. It is not CW right now. Maybe after 3 years we can show you. When it is pulsed, the energy from a dye laser can be to 10 millijoule. The pulse width can be, look at it, 1 nanosecond. These dye solution or conjugate polymer can be easily mode locked. Mode locked. If it is mode locked, you will get 10 femtosecond, 10 picosecond pulse. 10 picosecond pulse. Okay, that's a summary of these lasers. Now let us go to solid state laser. Solid state laser, there are two types. Insulator. The other one is semiconductor. Semiconductor. Insulator, the best example is neodymium laser or neodymium glass laser. This will produce laser pulsed or CW. Wavelength is 10.6, 1.064 micrometer. The power from this neodymium laser, if it is CW, you can get typically 5 watt. Typically you can have more also. This is the most common. If it is pulsed, the peak power can be 100 megawatt, 5 nanosecond. Not 100, let me put 10 megawatt, 5 nanosecond. This is the typical value. There are other insulators laser. The next most important is tie sapphire. This neodymium laser you have seen. Next week you tell me we have a neodymium laser and then you have a tie sapphire laser also. Remind me, I will operate that one also later. Right now it's not okay, but I can make it work after some time. I will show you how that laser also works. So you will see experiment, you will do some experiment with this YAG laser and the tie sapphire laser. Okay. This tie sapphire laser is the only tunable laser. And this is tunable from 800 to 1000 nanometer, approximately. I would say 960 nanometer.
Dr. Tunable, we control the from 900 to 9. Just
You can tune it.
Just
You
that's
can tune it.
any process to do this, or
What is it?
any process to do this, or we can control it easily.
I shall explain. You can tune it like you tune your radio. How it is done, I shall explain. Okay. We will come back to this one. Then let us finish this one. Again, it can be CW or it can be pulsed. Tie sapphire laser. Look, this is in the infrared. This is in the visible region. Now look at this one. This is the laser, tunable laser in visible region. So you can say that dye solution laser is the best tunable laser in the visible region. And tie sapphire is in the infrared region, near infrared. And that is the only tunable laser. There is another tunable laser, but don't worry, only this is marketable. Next important is semiconductor laser. In this, it is there are so many semiconductor lasers. It can be pulsed or CW. You can get semiconductor laser now these days from 400 to 3000 nanometer. One such laser already you have seen the last lecture. I showed you the violet laser. You remember that?
Yes.
Then I showed you a red laser. All of them are handheld semiconductor laser. The speciality of this kind of semiconductor laser, these are based on current injection. Current injection, battery operated. I can put a laser in my pocket and go do long jump, high jump. When I say long jump, if it falls down, don't worry, it will still work. None of the other lasers will work. All of them are very fragile. If it falls down, this Heaney laser, just drop it, that's all. It will never work.
Finish.
That's the end. Whereas with the semiconductor laser, I can jump up, I can break. Not only that, you can give it to the child also. Don't give it to the child. It will not give a shock because the voltage is only 10 volt. This is 2000 volts. That examiner laser, 20,000 volts. If you ever have an electrical shock, that will be the last shock in the life. Okay. It can be CW and the power is usually from one diode laser, semiconductor laser. Usually we get 1 milliwatt to 50 milliwatt. We don't go more than this. If you want more, you can put a diode array about which I have given lecture last time. Apart from all this, there are few very important areas. Yes, Prof. Okay. Okay. Where did we stop? No. All these lasers so you have seen gas, liquid, solid. There is one more laser which you may call as a plasma laser. What is a plasma laser? What is a plasma laser?
Produced from separate ions.
Okay.
You told us we use laser to produce plasma.
Yeah, that's another story. Okay. But how to get the laser from the plasma? I tell you something. We don't really call it a plasma laser. This is called a free electron laser.
Need
The same.
high vacuum and high power electric.
Accelerated electron by
Yes,
magnetism.
the free electron laser. Why it is called a free electron is all this from gas, liquid, solid, everywhere, the electron is bound to the nucleus, so it forms an atom, ion, molecule, whatever it is. The charge is bound to the system. Since it is bound to the system, you define certain quantum states. In free electron laser, the electron is not bound to this atom. It is free to do anything. Okay. How we do that? Look at this. We have a long tube. We start with the free electron obtained from an accelerator. So the accelerator, you have electron coming out like this. You direct it. So the electron has a high energy since it is from the accelerator. Then what we do, you apply a magnetic field, north, south. If I apply the magnetic field in this direction, the electron will be pushed like this. This is due to Lorentz force. It will be pushed like this one. Then what I do, I have another magnet like this. This is north, south. When it comes here, electron will be pushed like this one. So electron will move like a snake. Okay? Will move like a snake. This can be pictured like this. It is not in this plane, it is in this plane. You must move. Because we apply magnetic field in this, electron going like this means
Right.
it should be transverse to this, to this. This is called Lorentz force. The movement, the force will be B cross E. E electric field. B in this. When you put it across, it's a cross product of two vectors. It should be perpendicular to this one. You are right, like this. It is like this. This is electron, magnetic field. This is the movement of electron, mechanical movement. Since we alternate the magnetic field, so it will go like a snake. Whenever there is a change in the direction, this will keep on producing electromagnetic wave. Then what you have to do, you do all this one, put two mirrors, that radiation will come back, produce stimulated emission on the electron, interact with the electron, release the energy from the electron, so you will get laser. In this case, there is no such thing as a population inversion. Understand, for the first time, you don't see any population inversion, because whatever is the number of electrons which are coming here, they are put into certain dots. Okay, so this is something like, this is how any microwave works, only like this. This is the principle of magnetron. Now next, you should take it as an example. Take it as an exercise. How we produce microwave in a magnetron. How it is close to, or how it is similar to free electron laser. This particular free electron laser is a special kind of laser compared to all other types of laser. Next step. How can you, this is again a tunable laser. Tunable laser. How can you tune the laser? Very easily you can see. See, the electromagnetic wave which comes out as a coherent radiation has to depend on the electric field, magnetic field. Not really. It depends on the frequency of electric field and magnetic field. Once I have chosen an electron of certain energy, the velocity of the electron is fixed. But I can play around with the frequency of this one. So I can change the frequency of the magnetic field. Correspondingly, I can change the frequency of the laser that comes out. So it is tunable. Most of the lasers, free electron lasers, are in the infrared region or microwave region. Not much on the visible region. to produce visible region, X-ray region, all of them are possible. You need very high energy electron and very high magnetic field and very high frequency magnetic field. Since it is very complicated, since you need you need very high vacuum and high energy electron, all these things are possible only in a very big nuclear research laboratories. So it is not most commonly available. These are really classified. Why we say classified is, this one comes from an accelerator. All nuclear accelerators, all of them are a big weapon based one. So the whole process is classified, so we don't have much information, and these are not marketed at all. You cannot just market it.
They use it in weapon disease or
For army, maybe.
They use it in the weapon. They still are in the research stage. It is not doing anything. It's still a research stage. It has a wide range of application.
So here is a vacuum.
Huh?
Vacuum. Here, temperature how much?
Very vacuum. Very good vacuum.
Temperature around.
10 power minus 8 torr. 10 power minus 8 torr. Okay. Yes. I've given a wide perspective of a quick conducted tour of variety of lasers. Now comes the point. All these lasers are oscillators. Now what we are going to see here is an amplifier. Now the question is, what is an oscillator? What is an amplifier? All nonlinear lasers, all nonlinear phenomena, or all nonlinear optics, there is no population version. These are called amplifier, or even then, you don't even call an amplifier. I would say it's a frequency converter. Converter. Based on, remember, based on non-linear response, of the medium. This is the crux of the story. It is not the laser which is playing major role. It is the medium which is important. Depending upon the medium, I can get a different laser. Before going into the detail, most of the lasers are oscillators. What is an oscillator? And I put your question, why laser is called optoelectronic device? Why? I asked you to check this question, right? I asked you, gave you a question. Laser is an optoelectronic device. Why is optoelectronics? Any idea?
I tried, but I couldn't find that exact information.
Do you have any idea why it is called optoelectronics device? Sometimes it is called quantum electronic device.
quantum electron, because the energy depends on the you get the energy from the energy levels.
Okay.
That's the quantum electron.
Then you should say quantum device. Why quantum electronic device? You are right. Quantum, right. Why it's quantum electronics?
It's the electron, because the electron, the photon.
Where is electron there? Where is electron? It's a quantum device, clear. It is not the electron which is, it's a photon that comes out. Right? Whereas in electronics, in our mobile, it is not the photon which is running around. Your mobile is electronic device, right?
Yes.
Yes or no?
Yes.
What is happening? It is the electron going here and there.
Yes.
Photon is not going there. Then why you should call it a quantum electronic device? Let me explain what it is. See, electronics is an instrument or a device or a discipline which is based on movement of electron. Movement of electron. By the way, what is the difference between electrical engineering and electronic engineering? You have friends, students. There are two. If you go to engineering, some students will become an electronic engineer, some student will become electrical engineer. I leave it as a question. Next lecture, remind, tell me. What is electronics engineering? What is electrical engineering?
Electronics is the small device like semiconductors, resistance.
Very good. You are
But electrical like
The high voltage.
the voltage and
right. Okay, that is correct. Then another, there is still more important information.
and the electrical they are very large devices.
Okay, that's what you told me. Any other difference? There is a fundamental difference.
Maybe the media or the.
Okay, think about it next week. Okay, coming back. In electronics, it is dependent. The electronics depends on movement of electrons. If you consider a triode, or you can consider any diode. Look at this one. I have P, I have N junction. Then I connect to this. Right now, since I have connected N to this, P to this will start sending current. Current will flow. So it will be like this. Current will flow because this is forward biased. Then what I do, look at this one. Here I put an inductor, capacitor, then this will produce an oscillation. The electron will be going back and forth like this. If the electron is going back and forth, now let me explain at this point. Look at this one. Once the circuit is connected, without this you will get only DC. You will get a DC because the electron will start go and come back. That's all. The story is finished for this one. You cannot get AC. If I want to get a AC, what should I do? Look at it. I change this one. I put a capacitor and then I put an inductance. Then, as the electron go, rush towards this. As the electron start from here, go from here, then you will see the capacitance get charged up. First thing, capacitance will get charged up. So you will have a high potential between the two electrodes of the capacitance. Then what will happen is, this will start kicking back the electron back. As the electron back goes here, current goes here, the inductance will resist this one. So the electron will go here and here. It will be going between these two. This is called the tank circuit. Since the electron is running back between the capacitor and the inductor, since the electron is going back, you will have alternating frequency. This is called alternating current. This is the beginning of alternating current. Since the electron is going back and forth, this produces an alternating current So this is acting as an oscillator. Now in any oscillator, since you have to take the energy out, look at this one. From here you must have another circuit which will take the output out. This is output. This is called by mutual inductance. You will have an alternating current. This is how you take the output. Since you take the output, after some time the electron will lose energy. So you have to produce another circuit. You make some arrangement so that the energy that is produced, energy that is lost, is equally compensated. So there should be a feedback from this circuit to this one. Only then you will have a sustained regular oscillation. Now look at this one. For any oscillator, the electron oscillates between capacitance C and L. Understand?
Yes.
Inductor, capacitor. Okay? Then omega equals root of LC. You know this one. This is determined. This is determined by L and C. So this is one which selects the frequency. Frequency selection is done by L and C. This is step 1. Secondly, energy is fed back by this inductor, by mutual inductance. All this should be properly tuned. Look at it. When I say this one, you should properly tune such that for this particular frequency, this is producing proper feedback. This is what is happening in laser also. I described a simple electronic circuit. Whatever I described in electronic circuit, now I should tell you for a laser. Look at it. I have a medium. I produce population inverse. Atoms vibrate, produce light. Then, look at it. This mirror, the distance between the mirror will do the frequency selection. Because you have seen, for any laser, this represents emission profile. And then, depending upon the length, I will have, these are what we call cavity modes, which are separated by the frequency of mode is C by 2L. That means this is allowed frequency, this is allowed frequency, but this frequency is not allowed. So these are the resonant frequencies. That means the two mirrors does very good frequency selection, not complete, very good frequency selection. And then what we do, there is so much loss for the photons. Loss due to scattering, loss due to absorption, loss due to transmission. That means you will have loss. This is called amplification, this is the loss, and then you will see this mode this mode and this mode. Only these three modes will have proper feedback. Look at it. Proper feedback to go into oscillation. That means, in this case, L and C produce a frequency selection. The feedbacks provided by this inductor. This is true for ordinary circuit. In laser, the two mirrors provide the frequency selection and also they provide the feedback. Because of this condition, you get a sustained laser oscillation coming out. Then, you cannot keep on getting a laser without another source for giving power. I cannot keep on spending my money unless I get a salary. There should be some other source. Where is a source for power? Here and here. See, I am taking the output. Where is a source for power?
From the battery here.
Yeah, from the, where is a battery? Here you must have a battery, which I have not shown you, understand? Yeah, here is a battery. Yeah, here is a battery. This is the source of all energy. Where is the source of energy?
Maybe optical from lamp.
Yeah. You produce population inverse by optical pumping or electrical discharge, you do whatever it is. That is a source of energy. This source of energy, which is, I could say, is a direct source of energy, direct current, something like this, is converted into a light of very high frequency. Let me repeat. The energy for this comes from the 2-volt battery or a 100-volt battery. What we get from here is a electromagnetic wave of, let us say, 20 megahertz. This is how any electronic oscillator is designed. Am I understand? Look at this is 20 megahertz, but I start from 10 volts. This is what is happening in your mobile. Am I right?
Yes.
Yes or no?
Yes.
In your mobile, you have gigahertz frequency or a megahertz frequency. This produces so much only from the battery you have. This is a direct current battery, you get 20 megahertz AC. Same way, you use flash lamp or use anything, but what you get is a laser in high frequency. You get a laser, or this is an alternating AC, look at it, AC N. What is a frequency? 10 power 15 hertz. This is 20 megahertz, this is 10 power 15 hertz. That means this is an oscillator. Only thing, it is an optical oscillator, or that is why it's called optoelectronic device. Understand? Whatever we do in ordinary low frequency, in radio frequency or audio frequency or microwave frequency, we have just extended it into visible light frequency. That is why it's called optoelectronic device. Why it is called quantum electronic device?
Because the transition happened between quantized.
That's right. Here, this is electromagnetic wave. That is also an electromagnetic wave. But in this region, in this domain, it is the wave nature of light becomes important. In this region, quantum nature of light becomes important. You know, light has two components, two aspects. One is a wave nature, the other is a quantum nature.
As photon.
As photon. Occasionally, it behaves like a photon. In another occasion, the same light behaves like a wave.
Yes.
If the frequency is low, it is a wave. Frequency is high, it is a particle or a quantum.
Yes.
In all the lasers, it is a particle nature, quantum nature, which becomes more manifest. And the transition is from one quantum state to another state, but it is again doing the purpose or the features of electronics. This is called quantum electronic device. Understand? It is optoelectronic or quantum electronic device. Next is this. Next we will go. Last lecture I gave you a question. What's the difference between optics and non-linear optics? And non-linear optics. Where is the division? At what time you say this is a non-linear phenomenon and linear phenomena? I shall first explain how you get light from helium or neon or whatever is atom. Let us say hydrogen atom. Hydrogen atom. How you get light from hydrogen atom? It is like this. Imagine this is the nucleus of hydrogen. Here is only one electron. This electron keeps going around like this. Then when I send a light, this light is absorbed by this electron, goes from here to here, goes to the excited state. Then we say this is E1, this is E2. Since this is higher than this one, after some time it comes down producing a light. This is how you say light from hydrogen atom. Another way of representing the same thing is this one. You can say this is nucleus of hydrogen atom. This is the cloud of electron. And then when I shine light, what we are referring, the light has an electromagnetic vector, magnetic vector. It is the electric vector which will have a strong influence on this one because of this one. When this field becomes positive, the electron, look at this one, this is the nucleus, the electron will go like this. It will get distorted like this. You see that? The electron cloud is closer to this one. Attract. Then this becomes positive. When this becomes negative, what would happen is, this is nucleus, the electron cloud will go like this. So the electron cloud will be pushed back and forth like this. The center of mass of electron cloud will be pushed like this one. Because of this one, you will see electromagnetic wave going like this. When I shake electron like this, it will produce electromagnetic wave, not in this direction, always perpendicular to this one. So I will have a light coming out like this, light or any electromagnet. So I will get electromagnetic wave. Next step. Next step is this. When I push this one, this is called polarization, because I